So hi everyone, this is Sean Mullery from Electronic Engineering at IT Sligo, and what I'm going to be covering in tonight's lecture in machine learning is I'm going to be looking at generalizing models. So what the idea here tonight is to think about a little bit beyond just training a model, but to think about how that model is affected how that model performs when it meets data that it hasn't seen before. And the trouble is that when we're developing the models, it can be difficult to know what's going to happen when it meets something that hasn't met before. And obviously, in terms of autonomous vehicles, you can see how this is a major issue for us because, there can be lots of edge cases out there that can occur, that we can't maybe meet in training, and therefore how is our system going to perform in those cases? Now obviously that's a very complex system. We're going to be dealing with much simpler systems here, but the same sort of ideas will apply in terms of trying to determine how well our model is going to react when it sees something that it hasn't seen before, or an example that it hasn't seen before. So let's say that you've chosen your model. So you've chosen whatever type of model you want. You've gone and done your training. You've watched the, you've watched your training loss diminishing down as far as 0. So you've got some sort of a graph like this that you're watching, and you've got your training loss here, and this is time, or you can think of it as number of iterations, maybe, of gradient descent. And you're watching it go down, and maybe it's even reduced all the way to 0. Okay, so you're thinking, well, that must be great. Everything's perfect. But unfortunately, that's not necessarily the case at all. So this can be very much the same as a student who just learns off the answers in the back of the book. Okay, now maybe they learn off how to do the exercises to get the answers in the back of the book, or maybe they just learn off the answers. But one way or the other, in that analogy, you can see what's going to happen to that student. If they've just learned off the answers in the back of the book, they may well do okay in the exam. But if they're given different questions, and that would be the general strategy, that's why we give different questions in an exam, then they're going to find themselves in some amount of trouble. Okay, because they're not going to see exactly the same as what they've gone and learned off. Now, of course, if they've gone and learned the general principles and they've done lots of examples, then there's a good chance that they're going to do okay in the exam. But this is not what we're talking about here. So remember that when it comes to supervised learning, in effect, all we're doing is we're saying, this is the data and this is the answer. So it's really very much like just having the answers at the back of the book and go and figure it out from there. So you can see in this situation that what can occur is that if the model is good enough, what it will do is it will just learn off all the data instead of actually learning a model that data might represent the process that's coming from. So just like the student who has not generalized their learning, what they've done is they've memorized specific examples. And this can happen in machine learning, and it's called overfitting to the data. So in other words, our model has learned off the data rather than learning the general principles that have caused that data, so that it can then, when it sees the similar things again, that it knows what to do. Now, the opposite of this is underfitting. Okay, the opposite problem is underfitting. And this is where, you might have something like, let's go back and grab our diagram from previously. So just grab that. For some reason this never doesn't seem to work when I'm doing a recording. I'm not sure why that is, but anyway, we'll redraw it again. So again, we have our training loss here, TL, and we've got time. And what happens here is you've got a loss, and it's maybe reducing to a certain level, and then it kind of levels off, and it never gets down below a certain point. Okay, so this is called underfitting. And this is where you can't even seem to reduce your training loss to anything reasonable. And in machine learning, this is generally a symptom of not having a complex enough model. Now, in our analogy of the student, maybe not a great analogy, this is where the student is just not smart enough. Okay, now that, as I say, that rarely happens in the real world, that a student isn't smart enough. It's usually some other problem that's there. But in terms of machine learning, it can happen that we just don't have a complex enough model. Okay, so students not being smart enough are much less likely in the real world, as each of us has been given a complex model to work with, which is our brain. And each of us has been given more or less an equal brain, but it is true that some people's brains are wired up a little bit differently than others and have a tendency to spend much more time in certain areas than others. So it's very difficult to say when we get to 20, 25 years old, is it a product of we just don't have the right brain for the job, or is it that everything that we've done up to that point has not trained us for this particular environment? Maybe it's maths, or maybe it's languages or something like that. So other causes of underfitting in machine learning are poor training mechanisms, or maybe an inappropriate loss. So we're training to minimize the wrong loss, and our system just isn't able to do it. Okay, so lots of these things can cause us to not have a good model as well, or to have an underperforming model in this way. So this is a little bit like the student who has the perfectly good brain but sits all day in the library looking at social media or something like that and can't figure out why they still can't do the examples. And I'm sure you've found yourself in the situations where you're studying, but you're maybe not making good progress, and that's maybe you're just not studying in a good way. So we've the same situation can happen in machine learning. We could have the situation that the model just isn't the right type of model. It's not good enough. It's not complex enough for the problem we're trying to solve. Or we could be just training in a bad way. Maybe it's a bad mechanism that we're using for training, or an inappropriate loss function, whatever it might be. Each of those things can cause problems for us. So if we think about the example that we've looked at so far, such as linear regression or logistic regression, where we're using linear models, in those sort of cases, you were dealing with generally straight lines, and that is the simplest sort of model you can possibly deal with. So this is a perfect example of where your model may not be complex enough to actually do the job that you're trying to get it to do. So what happens when we want to go to a more complex model, and what are some of the problems that we can face? So I mentioned at the end of the linear regression set of notes that there are these things called polynomial models, where what we do is we have lots of weights, and the weights are applied to our features, different features of x. So if we just have one feature, but we take a squared version of that feature and we take a cubed version of that feature, then in those cases we can have a much more complex model. So if we think back to the example that we used, where we had something along the lines of the weight of the turkey as being a feature, or if we take the brightness of a pixel as being the feature, then what we can do is we can match different weights up to different versions of that feature. So the feature itself, we can start obviously with a bias of some description. Then we can have the feature itself, which is what we have in this particular case, or we can have the feature squared and the feature cubed. And these are known as polynomial models, and they allow us to kind of map onto curves, onto some sort of curved shape, which can be quite variable depending on what the different weights at different points are. So that gives us a good bit more freedom, but obviously it's a much more complex model. So where previously for the linear model, we only had two weights, or maybe only one, now we might have 3 or 4 depending on, and of course we can go up to x to the power of any value of n there. And of course, if we've got more than one feature, this becomes even more complex again. Once again, here for this example of just 2 features, we've got our bias. We've got our first feature on its own, so we have to have a weight for that. We've got our second feature on its own, and we have to have a weight for that. We then have the 2 features multiplied by each other, and we have to have a weight, obviously, to control that, how much of that we're going to have. Then we have the first feature squared, and a weight to control that, and our second feature squared, and a weight to control that. And this can go on if you've got more features, or if you want to have cubic terms, or anything to the power of n. You can see how very quickly we add to the number of weights that we're going to have in our system. And of course, this makes our model much more complex than what we would have had originally. So how do we go about this whole idea of deciding what sort of complexity to have for a model? And then, of course, what are some of the problems that are associated with that? That's something that we have to kind of look at tonight. So let's take the regression example that I gave you in the first lecture. And we could use a very simple model for this. So we could just do a straight line like that, maybe something like that. In fact, that's not even perfectly straight. I think it's got a gap in it. So maybe that's a straight line, and you can see that we're going to have, obviously, this would be a perfect example of underfitting, because as you can see from the data, there is a kind of a curve in there, and this straight line is not taking account of it. And if we went further and further, you can see that that straight line is going to go up in this direction, and our dots are going to continually be below that in some way. So you can see the sort of problems that we're going to have. What we can also do is obviously we can, we could have an even simpler model than that, which is this one that, sorry, we'll just delete that. So let's say, for example, that we take this one and we say we're only going to have a single one, so it has to actually touch off the origin there, and then you can see the sort of problems that we're going to have. I can't do any of my resizing or otherwise here. I must try and get to the bottom of that, guys, whatever it is. So we have those sort of models. Now the next thing then is if we go for a slightly more complex model, like the polynomial. So a fairly simple polynomial might allow us to do something like this sort of curve here. Okay, so it might allow us to go up in that sort of direction. Now that's not exactly the same as what we saw from the example where a particular practitioner had gone and tried to figure out what exactly is the right results for cooking a turkey. But it'll probably do a reasonably good job of modeling it. So fairly, with a small number of quadratic and maybe cubic terms, so to the power 3 terms, we can probably get a fairly nice curve like that will follow the data reasonably well. But you might still say that that's actually fitting it quite well, okay? Rather than it being either overfitting or underfitting, which the linear model would have done. Now the problem is if we go up to much higher levels of polynomials, so let's say you're going to have x to the power of 5 and x to the power of 10 and so on, all the way up there, what's going to happen in that particular case? Well, what's going to occur is the model will try and fit each of the different points, and it'll start going like this, basically trying to get through every different point, all of them, and it'll start doing this sort of thing, like oscillating about, basically trying to touch every different point as it goes. And the reason that it wants to do that is that when we calculate the loss of it, if it touches every point, then no sample is actually going to be giving it any value of loss because it has touched every point. And that would allow us to get our loss all the way to 0. Okay. But the problem with this is that this is overfitting, because all that has to happen now is some new value comes in here like that, and it doesn't touch the data. And what's more, it's now a very complex model, and it's giving a big loss for that. So it's telling us that we're going to have to be at some other point. And the worst that can happen with this is that depending on the way that our polynomial function works, sometimes in order to hit every point, it often has to go a long way off. Okay, so it has to come from a very long way back in order to touch different points. Now the problem with that is that then our model might say this is our prediction, which is way off, but it actually matches the model, and you can see the sort of problems that we would have there. So this is called overfitting to the data, and it can give us a very complex model that really does not properly tell us what we're looking at, that would not give us a proper prediction of what it is we want. So that's not a good model either. The trouble is, if we can't visualize the data, which can particularly happen if we're up in higher number of features, what do we do in order to try and pick the best model in order to make sure that we don't have either underfitting or overfitting? Okay. Classification example then, of course, is obviously we have a straight line, which would just go straight through like that or something like that. But then you've got a polynomial model that's going to come along and say, well, okay, I want to fit all the way around this data here and come back around to there, and it might even do something worse than that, in order to maybe make just much worse of a classification problem. And that then means that if we have a point along here somewhere, we might well say, well, that's on one side or the other side of the barrier when we're doing it, and it may indeed be incorrect because it's followed a much more complex model than it needed to. So one of the major problems with this is with overfitting is that it doesn't just misclassify some of the time. That wouldn't be so bad, but it can often do so with a very high confidence. And what this basically means is that we get an idea, we get a suggestion of, let's say it's a classification, and we say, well, it's class 0 or it's class 1. And it can often say that it's very, very confident of that. Whereas our simpler model might say, okay, I think it's this, but I'm not very confident. Obviously kind of personifying what the model is going to do. That might be what it would tell us. and it could often be very useful to know that it's not particularly confident of the thing, because our model, it can be useful just to be able to tell that this might not be a trustworthy prediction. The problem with an overfitting model is that it might say, it might get the prediction wrong for starters and be very, very sure of itself. And those two problems are equally as bad as each other. So when the model is even more modest, when the model is of more modest complexity, it may have certain samples in the training set that end up on the wrong side of the decision boundary, a classification, or a long way from the model in regression. However, the model can report that. It can kind of say to you, look, I'm unsure about these particular ones. It can say that we predict this, but I'm only X% sure for classification, or with a certain tolerance with regression. But with overfitting, it tends to be overconfident as well. So, for underfitting, how do you deal with each of these problems, firstly, if you do have them? Okay, so for underfitting, you can either train for longer. So if you have a complex enough model, but it hasn't trained very well so far, you can maybe train for longer. Or you can try and get maybe more data. Each of those will be quite useful to you. You may train for longer, but if your model isn't complex enough, it may bottom out and not go any further. So that's one of the things to test first. And generally speaking, it's a good thing in machine learning when you're trying to find the right sort of model, is that with a small amount of data, and this is a trick that a lot of people use in deep learning in particular, is that they take, rather than the full of ImageNet, they might only take 1,000 images. And your model at that stage should be complex enough to be able to actually memorize all the images effectively. If it's not able to do that, the suggestion then that it's going to be able to model your problem when it's dealing with 1 million images is unlikely. Okay, so it's often a good thing to underfit it first, or say to overfit it first, to show that it can be done with a small amount of data. So what you can do is you can add data. I don't think I've actually wrote that down there, but if you can add data, that's a good thing for underfitting. Okay, that'll help the situation. Or you can go for a more complex model as well. Okay, so if it's clearly bottoming out and not getting any further, you can maybe try and go for a more complex model. You can also you may also be required to look at your training mechanisms. Are your training mechanisms appropriate to the problem? Is the loss function appropriate to the problem? Now, if for overfitting, then the opposite problem, one thing you can do is you can make your model a little bit less complex. So you can, looking back at our situation there with our polynomial, you can decide, well, I'm not going to go for the one that's too much of a straight line. And I'm not going to go for the one that's got too many higher order polynomial parts to it. What I'm going to do is I'm going to go for something in the middle there. Okay. The other thing you can do is, particularly if you've got a problem that's got a lot of features in it. Okay, so the ones that we've looked at so far, we've maybe only had 2 or 3 features, or 1 in most of the cases. But if you've got a lot of features, and in particularly if you've got a large number of features compared to the number of training examples, okay, so if that's just not a big enough ratio, that you haven't got 100 times as many samples as you have features, then generally speaking, you can be running into problems there as well. Remember that for each feature you've got to have some weights to go with that. So you end up with a lot more weights, and with a lot more weights, you've got a much more complex model. So the more features you have, generally the more complex the model as well. So you can try and drop some of the features, but there are some issues with this. If you're dropping features, you're also dropping information. So you need to be a little bit clever about what sort of features you're going to drop. You need to maybe look at the particular problem that you're trying to solve and say, well, are all of these features relevant to my problem? And you can try and choose some of them that are not relevant, because of course the problem that a model faces when it's optimizing is that it can't really tell which features are important and which are not. And so small little changes in a feature that may have no correlation with your output can often still lead to a situation whereby you don't really know, whereby you know that it can lead to a situation where small little changes in something that's not correlated with it can still have an effect on the output. So it can sometimes be a good idea to drop features that are not important. The bottom of it. Okay, so that's fine. So sorry about that. So so I was mentioning here about decreasing the number of features, and I was saying that some of the features may not be important. The trouble with this idea is that if you make an assumption about what features are not important, you rule out the idea that the model may find something that you as the human don't realize that there's a correlation. Okay, and a lot of what we do, particularly in unsupervised learning, is we're looking for correlations in data, between data and labels, that we aren't aware of as humans. Okay, so that's the danger with this idea of just decreasing the number of features in order to deal with underfitting. But it can be quite powerful, and of course what it can do is it can make your model a little bit simpler, and it'll train a little bit quicker. So it's not to be ruled out by any stretch of the imagination, but it's one to do with caution. Now, the final thing that we would do generally, if we're dealing with overfitting, I see that I've kind of put the two of them on the one slide here. The final thing to do with overfitting, which we're going to spend a bit more time on tonight, is to use the thing called regularization. Okay, and I'll be explaining more about what that is, as we go through the slides tonight. So, when it comes to deciding on the complexity of the model, how do we decide on let's say, for example, that we decide we want to go a little bit beyond a linear model up to something a little bit more complex. How do we decide how far to go? So when dealing with relatively simple models that take only minutes or hours to train, you can afford to try many different model sizes. So this means that you can try a polynomial of degree 1, degree 2, degree 3, degree 4, degree 5, maybe up to degree 10, if it's only taken a few minutes to train your model. Now, of course, the more parameters you've got in your model, the longer it's going to take to train. But if it's still only taking a few minutes, then that's probably time well spent. Do bear in mind that when you get into the sort of deep learning models that work on, for visual recognition, oftentimes they can take 2 weeks to train. And so when it comes to doing a lot of the things that we'll talk about tonight, you kind of have to choose either not to do them, or choose to spend a year doing them, or choose to go to a company like Google and work for them, who have just got huge resources available to them to allow you to do to allow you access to enough computing power in order to do the sort of things that we're talking about here tonight. But for small models, you have quite a little bit to play with in terms of the amount of time that it's going to take. But you can't just pick the one that gets the lowest training error. That's the problem. So in other words, you try polynomials of loads of different degrees and size, and you might think, well, I'll just check which one gets the lowest training error. That won't work, because the chances are, as we've already explained, that the highest order polynomial will get you down to the lowest training error. And we've saw that that's overfitting. So how do you recognize when overfitting is taking place in order to try and get rid of that? So instead, we need a mechanism to check our loss on data that the training algorithm doesn't see. So what we're talking about here is that we're going to train on a certain set of data, and then we're going to test it on another set of data, which must be similar in certain ways that we'll come to in a moment. And we will use that second set of data in order to determine whether we have generalized well. If we've overfit, it will not do particularly well on that second set of data. If it's underfit, it won't do particularly well on the training data, and probably not on that second set of data either. Okay. So the technique we're going to look at first is something like hyperparameter tuning, which is this idea where the hyperparameters that we've mentioned before that you normally need to make a decision on, we're going to try and run those a few times to see what's the best hyperparameter to choose. So hyperparameters, as we mentioned before, are parameters that are chosen rather than learned. And some examples of hyperparameters we've seen so far might be the degree of your model. So what degree of polynomial are you going to pick in order to do it? Is it going to be a linear, quadratic, n-degree polynomial? What is it going to be? We saw that the learning rate, alpha, was a hyperparameter, although we probably won't have as much issue with this particular one in terms of trying to validate it. And I mentioned regularization already. We're going to come to it later, but the amount of regularization that we have is normally controlled by a parameter called lambda. And again, how much of that to use is another hyperparameter that we have to choose. And therefore, it might be nice to have some idea of what's the best parameter to choose. So by tuning that, by trying to pick the exact best value. So let's say we're trying to tune the degree of the polynomial, for example. So the plan would be as follows. And by the way, I should say, particularly if anybody's just watching this in a few years' time on YouTube, or you're maybe just watching the recording quickly coming up to an exam, don't just take this slide on its own, because it's incomplete. I talk here about splitting in two, and I'm actually going to split in 3 in the long run. So don't take this as the complete word, but we're building up to where we're going. So take whatever labeled data we have and split it into 2 categories. Training data, which let's say we'll give maybe 70% of the data to training, and validation data, which we're maybe going to give 30% of the data to our validation. Okay. Now what we're going to do is we're going to create models with increasing degree of polynomial. So let's say degree 1, which is just a linear model, degree 2, degree 3, degree 4, degree 5, and so on. We'll set a limit somewhere, but we can try a few different ones. We'll train each of them until they converge. With that basically means until their learning rate, or until their loss goes no lower on our training data. So it'll level out in some way. So train each of them until they've converged at that point, using the training data only. And as I say, don't be surprised if by increasing the degree of the polynomial, this gives you a decreased loss at convergence. In other words, that the loss is lower. That's not necessarily a good thing, as I say, and we'll see why in a moment. So now what you're going to do is you're going to validate the data. And when you're validating the data, you're using your validation set, which we have here. You're using that validation set, but you don't train with that. And what I mean by you don't train with it is you calculate your loss with the validation set, but you don't update your parameters. Okay, because you don't want to learn on that validation set. You only want to use that to determine how good is your model when it comes to data that it hasn't seen. If you go and learn on it, then it is data that it has seen. And that's the idea. So it's a little bit more complex than this final sentence. So that's why I say, wait until the end of the lecture before fully judging this. But the one with the lowest validation loss would be likely to perform the best in the generalized setting. Okay, so what you might find is a situation where, due to the different degrees of polynomial, we get a lower and a lower and lower rate at convergence, but that somewhere along in the polynomials we find that our validation error goes higher. So we might see that it goes something along the lines of going down the way as we increase in polynomial, increase degree. That we might find that at some stage actually that error starts to go back up again, and that's because we're managing to overfit the data, but because that polynomial has swung to different places in order to do that, it's actually giving us a worse error on the validation set, because that's training it, or that's data that it hasn't yet seen. And therefore we might be saying, well, okay, the lowest point of this in our validation one might be the best place to go. It's not quite that simple. We wouldn't just use that, because the validation set is normally a good bit smaller, but it might suggest to us that that's the right set of parameters to choose for our model. Now, we need to be a little bit careful here. I said that the hyperparameters are parameters of the model that are not trained, but we actually just go and choose them. Okay, so somewhat arbitrary. But then I said that with this method, we're going to tune those. So there's a little bit of a contradiction here, because if we're tuning them, we're not exactly picking the value ourselves. We're running through a set of versions of the system, and we're trying to figure which is the best set of hyperparameters to choose. But it's not really us that's choosing it, it's the validation set that's choosing it for us. Now that's not quite the same as training, in that we're not doing something like gradient descent on it. But nonetheless, we're choosing it based on that validation set. So there's a signal that's coming from the validation set that is determining what is the correct values to use. I'll just maybe start again on the slide. So what we're saying here is that hyperparameters, they're parameters that we're supposed to be choosing rather than training on. But the problem is that by this method of hyperparameter tuning, the validation set is in some way training, is in some way getting involved in the training. It's not training the actual weights of our network or of our model, but it is in some way affecting those hyperparameters. It's not training them via gradient descent or anything like that, or any of those algorithms, but we're using the information from it to choose it. And so therefore, our model is affected by whatever is in that validation set. And as I say, when you do maybe something like a midterm assessment, and the whole idea of that is for us to get a mark associated with your learning to that point. It's not meant that you're meant to learn from that, but you can't help but learn from that. from that exam. You've seen those questions. You know what mark you got for them. Now you have an idea of how to change given that information. So very similarly here, your validation set is now compromised in some way. So it's not really, because of the fact we've used it for tuning our hyperparameters, it's not a perfect score of how good our model is in general. Okay, what's happened is that we've tuned our hyperparameters on it, so it's the best one for our hyperparameters, but it's lost the ability to tell us about generalization, and that's a problem. So the tuning that takes place is in some way using the validation set. It may not see the data directly, but it is getting a signal from it. In effect, the validation data is compromised, and if it doesn't give us a true picture of the generalization of the algorithm. So for this, we need a test set so that we can calculate the test error. And this is what I said to you earlier, that if you just stopped on that slide previously where I said we divided the set in two, you don't have the full picture. You haven't learned everything that we need to do. So the thing about the test set then that's separate from the validation set is that you really need to guard the test set carefully. You really need to protect the test set from yourself. Okay, because you're the one that's likely to do damage with the test set. And you should use it only sparingly. Again, a little bit like the student who has the answers at the back of the book. The ideal way to learn is to not look at those answers and only check them when you've already attempted the problem. But if you've attempted the problem and then you go and check them and you realize you're wrong, you've now got some information from that back of the book that when you go to attempt it again. And therefore you can see how those are then compromised, and you'd need a new set of questions and answers that are really going to help you to learn. So the test set is something that we would normally set aside for ourselves and try and use really, really sparingly. The difficulty is that you either go down the road of using it so sparingly that it becomes unuseful, or using it too often and therefore it becoming compromised. Where the model in some way has got information about the test set, even though it hasn't got it directly, it's got it by this indirect means. So the test set should be kept apart and almost never used. In fact, really the ideal place for it to be used is for you to test between maybe different algorithms that you might be using, or different models. So once you've gone and trained and done your validation on a model, you might be trying some other model somewhere else on the same data, and then at the end you do a test between the two to see which of them comes out best. Now the ILS VRC ImageNet competitions, the organisers actually keep a test set that no one ever gets to see. I think Kaggle competitions do this sort of thing as well. So now we've got a situation where we might ourselves, in order to determine where we are, divide into training, validation and test, and then we find out that somebody that we're submitting it to also has a test set. So you've got this further degree. And the thing is that test set begets test set begets test set. It can kind of go in very easily in that manner. But at some point, once we're tested, then that test set has a tendency to become contaminated or compromised. So your model is tested on this test set that nobody ever gets to see for this particular example. Your model is tested on it. You submit your model and they do the testing on the test set. So you never get to see that test set. They just give you back your score later on. You get the results, but you never get to see the test sets. You might say, well, okay, how is the test set compromised at that point? Well, this may be the best way to find out who has built the best generalized algorithm. But even in this case, if people make enough entries, or indeed when let's say I decide I'm going to build a new model that's going to compete on the ImageNet competition. Well, what am I going to do? People have published the model that they've done previously. And what's more, they've published the score that they've got on this test set. They haven't seen the test set, neither have I, but I know that their model does well on that test set, and I know other people's models do not. And so it quickly gets to a point at some stage where actually we're judging models based purely on that test set rather than maybe on how good they are in a general sense, because they're all being tested on that same test set. So you can see the sort of problems that can occur. And this has indeed kind of already begun to happen with ImageNet, where they're really saying that actually that test set has already been compromised and we now need to come up with a new test set that's kind of outside of what ImageNet is and therefore tries to test that generalization. So there are an awful lot of models at this stage that have gone a little bit beyond the generalization and are just a bit too good at the ImageNet set. So this is why it's vital that the test set is usually used as sparingly as possible, because it'll damage you yourself, and it's you yourself that really have to keep this separate. So normal set of circumstances, but really depends on how much data you have, we normally like to split our labeled data into three. Training set, around about 70%. Validation set, maybe around about 20%. And a test set, around about 10%. However, the thing is that does also depend on us having a large enough set of data that these numbers actually make sense. If it turns out you've only got 100 samples of data, well, that's not really going to be a lot. You've now got 70 samples for training, only 20 for validation, and only 10 for test. And it's very difficult to say that the test set is then going to fully cover the whole distribution that will be covered by the entire set. A few important things here. You should also make sure that your data is not ordered, i.e. it should be random. Now, just to be careful here, what I mean by this is that in most of the cases that we're dealing with, we're not dealing with data that goes one after the other. There are systems for doing that. There are things like long short-term memories, LSTMs, recurrent neural networks that look at, let's say, text or audio processing, where the context and the order that it comes in matters. In most of what we're going to be dealing with, the order does not particularly matter, or it shouldn't matter, and therefore our data should be in no particular order. Now, the problem is, even in the example that I'm going to give you for your first assignment, which hopefully I'll get out to you this week, and then I'll maybe try and take some time next week to talk to you about it, that data is actually ordered by time. Now, we're going to have to try and ignore that to a large extent and pretend it's not. But one of the difficulties that you're going to fall into is that you need to make sure that when you're doing this split here, that you split it randomly. You don't just say, I'm going to take the first 70% and they're going to be my training set. The next 20% is my validation set, and the last 10% is my test data. The reason for that is that you may find that if they're ordered by label, for example, you may find that one of the labels only turns up in the test set, and the other labels only turn up in the training set or only in the validation set. And therefore, you don't have an identical distribution of them all. So it would be very important that you randomly choose those. And generally speaking, you'll find that things like scikit-learn and some of the other libraries there, so everybody has had the same problem before. So there's generally library functions there for doing these splits, or there's or it's part of the training in the particular thing that you can tell it what sort of split you wanted to make, and it will do that split for you. So make sure you look into that before you reproduce the wheel, or reinvent the wheel, because the problem, while it can be very good as a learning experience to reinvent the wheel, there's also a much larger chance of you introducing a bug into the system. So particularly in a system whereby you're going to try and deploy it somewhere, you want to use as many libraries that have been rigorously tested by people and have as little of that has been newly developed that has not had the bugs ironed out of it. Because one of the things about machine learning, deep learning in particular, is that debugging it can be very, very difficult indeed, and it can be very difficult to find that you've got a bug at all. So for that reason, you want to as much as possible use libraries that already exist, because they've probably been tested by people to a significant degree. One thing to point out here, there's a particular term called IAD, which is independently and identically independent and identically distributed. And what this means is that if we were to look at your distribution of data, let's say it follows some sort of a Gaussian distribution like that, and this is your training data. What we would expect to see is that your validation data, you mightn't have as much of it, so it might be a bit more messy, but you'd expect that it's going to follow as something similar. And then your training data might be even worse in terms of its messiness, but all the same, it still follows roughly the same distribution. If you saw that your training data only covered a section like that, well, then clearly you've got a problem. It's not covering the same, it's not distributed in the same way. The independent point means that each of the points should be independent of each other. In other words, that your samples should not be dependent on the sample that came before and the sample that came before that. Now, as I say, in the example I'm going to give you, we're just going to have to pretend that it's that's not the case. But do be aware that if it is the case, that can have an effect on your model that you're going to do. Okay. Now, So I've been talking quite a bit up until now about regularization, saying that I'm going to come back to it. This is an important part of any sort of system that we're going to build. Now, regularization is a more general way of avoiding overfitting. So rather than us having to be too concerned about, let's say, the degree of polynomial that we're going to do or the complexity in the model, as long as our model is complex enough for it to overfit, we can use something like regularization to try and stop it from overfitting automatically. So rather than us trying to reduce the features or get more data or reduce the complexity of the model, instead we put in this regularization term and we optimize with this regularization term there, and that then basically stops the model from becoming any more complex than it needs to be to solve the problem. The difficulty is that we have to include a hyperparameter with our regularization. And of course, once it comes to a hyperparameter, we need to either tune on that hyperparameter or choose a good hyperparameter. And that's going to choose the level of regularization that we're going to have, and hence the trade-off between overfitting and underfitting. Okay, so there's nothing ever works perfectly in this that is going to do it itself. So it works by adding a term to the loss function. We'll see an example of this loss function in a minute. And that what it does is it adds loss to the model if the model is not of the preferred type. In particular, we want the weights to become we don't want the weights to become very large. Now, we don't want to get too deep into this because there's a lot of discussion when it comes to what happens when weights become too large. But any of you who have ever done any control systems or maybe digital signal processing in the past, you may have done things like pole zero diagrams. Now, I'm not asking you to remember them, but has anybody done that sort of thing, pole zero diagrams, where you had to plot poles and zeros when you were designing systems? Yeah, okay, so Brian did a long time ago. Okay, so don't worry too much if you haven't, but you may remember in those that you had to plot things on particular sides of the diagram in order to design the system so that it didn't get out of control. Because control systems, of course, can oscillate out of control. Filters, can also oscillate, that they become a larger and larger value coming out. And the problem always with those ones was that you had a feedback system. And in that feedback, if it was negative feedback, it would always cause the system to go down over time if there was no new input. But if it was a positive feedback, it would cause the system to run away with itself. Now, when it comes to training weights, our weights are part of a feedback system because we're getting a signal on the loss and we're feeding back in order to try and do something. So the problem that can occur is that if you have some very large weights, it only takes a small change to cause the weights to jump very quickly in one direction or another. And that can very quickly cause some or a lot of the weights to suddenly get very large, very large, and very large, and we end up with major problems with our system. Okay, so generally speaking, it's a good idea if we can keep all our weights smaller. And so one of the things that we can do as a regularization is we can penalize the weights for being too large. Okay. We won't go into it in any more detail than that. You can just kind of accept the idea that if we keep our weights smaller, that tends to simplify our model a little bit. So it stops, let's say, higher degree polynomials causing major swings to occur and that sort of thing. Okay, so there's a lot of different reasons that we would do it, but it's all to do with kind of keeping the thing stable and stopping it from changing too quickly, and therefore finding an unusual or a damaging model. So remember that training of weights is based on a feedback mechanism. That the change that a weight undergoes in each training iteration is partly dependent on the size of the weight. A large weight can change by a large amount very quickly. So you may think this won't matter because it is the same for all weights, but as the differences in the magnitude of the weights can quickly spiral out of control, individual weights' influence can quickly exceed their importance. So for this reason, we add a penalty to the loss function that is related to the size of the weights. And you'll find that there's a system later on which we call weight decay, where over time we continually start dropping the value of the weights while we're training, and this also has a tendency to keep things in line and keep things under control. So here's our standard function that we used, which is our squared error loss that we have there. And so we can see that this is our prediction and this is our label. We take one away from the other and we square it, and basically this would over time tell us what the loss of our system was. In other words, how different were our predictions from our labels. But what we're saying now here is that we're also going to add in this loss here, which is a loss that's based on just adding up the value of the weights. So if the weights become larger, this loss becomes larger. The only way to get this very, very small, or to get it to 0, is to make sure that all our weights are 0. Now clearly that would be a problem as well. That's unlikely to do anything. So if our weights were all 0, then this would be the bigger penalty. So you can see that these two are going to work kind of with each other. It's going to say, look, I'm going to allow you to reduce this, but only insofar as you're allowing the weights to stay in a small value if you can. If you can't, one becomes larger than the other. Now the problem is then we say, well, okay, how seriously do we take this term? And how seriously we take it is determined by the value of our lambda. If we set that, let's say, to 0.01, what we would be saying is that the weights of our system, the size of the weights of our system, are only 1% as important as the loss that we actually calculate, our squared loss. Okay, but if we set it to 10, we would say that it's 10 times as important. A lot of that would depend then on how big the weights are likely to become and so on. So there's no straight answer on kind of what sort of range that should be in. But you can see here that by setting our lambda higher, what we're doing is we're making our system simpler, okay? Because we're not allowing our weights to change by much, and by not allowing our weights to change by much, we're not allowing our system to become too complex. So the higher the value of or if we use a large value of lambda, that moves us in the direction of underfitting, where we have a simpler system. And if we use a small value for lambda, it moves us in the direction of overfitting. So if we have a value of lambda that's going to be 0.0001 or something like that, then we're likely to move in the direction of overfitting. But again, that depends on the size of the weights and a lot of things as well. So we can't always assume that it's a specific number, more just that if it gets smaller. One other thing to mention here is that we don't include the bias weight usually in regularization, so hence we use the n-1 rather than m, so we only sum up as far as there. As I say, it's a trade-off between underfitting and overfitting. So again, I'm not going to go through the actual calculation of this, but when it comes to doing our updates with regard to regularization, so updating our model and updating our weights, what we do is we simply include that term. Because the term is just added in there, then that means that in a derivative we can treat these two separately and basically just get the partial derivative with respect to the weights of that regularization term, and that comes out as this here. Okay. So that's part of our update. Then that's what we're going to do when we actually add it as part of our algorithm. And as I say, in many situations that will be developed into the libraries that are there. But it's good to be aware of the things so that you can maybe test a few samples to see if it's working correctly. So we can see that the regularization is a function of the weights W and therefore should be included in the update algorithm. For example, gradient descent. We can simply add the partial derivative to the rest of the partial to the rest of the partial derivative, so this is what we would get. It should be pointed out that this is the loss function that we're referring to here, but when it comes to determining the loss for, let's say, validation or for test, it doesn't make sense to include this term at that point, okay, because we only want to find out how well we're doing. So again, when it comes to comparing our training loss and our validation loss, this is the loss we would use for updating, but when we want to know how well our training is going, we would probably only use this section here rather than also using the regularization. So it's important to maybe keep those separate in terms of giving us a signal as to how well our system is going, because we don't necessarily want to include the regularization in terms of finding out how our training loss is going. So when it comes to testing and validation, with validation, we use the validation set for validation only. So we make our split, let's say it's 20%, and we just use the validation for validation only. But there's another system called cross-validation. And here what we do is, with cross-validation, we split the training set into train and validation. So let's say 70% train and 20% validation. And we do that randomly. And we train on the training set and then validate on the validation set. And then what we do is we repeat the process where we take the 90% that's there, ignoring our test set, that's completely separate. And what we do is we do a different random separation of the train and the validation, and we train again and validate again, and we do this a number of times. And the idea here is that we make better use of the data by doing this, and we take the average at the end as to what way we've what has been the training area and the validation error. The other system then, and there's quite a number of systems around here, so I'm really just giving a kind of a brief overview, but another system called KFold cross-validation. And with KFold cross-validation, we make a defined split, so no longer a random split. We decide certain samples are going into one, certain samples are going into the other, and we kind of keep note of that in order to make sure that we can be sure of it later. So we make a defined split of the data into k equal sets. So let's say k is equal to 3. We divide our data into 3. What we then do is we repeat k times the training and validation with each iteration using a different 1 divided by k validation section of the data, and the other k minus 1 divided by k for the training. And this way every sample is used for both training and validation. And then we take the average of the train and the validation scores. But there's quite a lot of work that goes into this. So maybe just draw this as a diagram. So that didn't work very well. Okay, so we'll have 3. This will run 3 times. So pretend that goes like that, and another one there. Now, so this is, we'll call this run 1, run 2, and run 3. And what we would do is we would split this into, I'm not done a good, there and there, let's say, 2/3, there and there, there and there. And what we would do is we would set this set here to validation, okay, or so I'll write it here as train, and we'll just set validation there, okay. And then what we would do is we would set train there and train here on this one, and set our validation here as this one on this case. Okay, so we would train on those other, we train on this one, and then validate on this one in the middle. So there's a validation set again, and then finally we would set this one here as our validation and the other two as train, and go again, and then take the average of these 3. So by doing this, all of our data is both used for training and for validation, and this can give us maybe a better sense of how it's going to, not so much how good it's going to generalize, because we'll use our test set at the end for that, but this will tell us maybe the best parameters that we could choose by doing this particular type of KFold cross validation. Now you can see that each of this takes time in terms of training. So if your training time is very, very long, this can be quite cumbersome to do. But this is the best. Now the ultimate version of this is called leave one out. And the idea is, let's say for example that you had 1,000 samples that were made up both your train and your validation set. And what you would do is you would use 999 of them for training and just 1 for validation. And you would then run that 1,000 times using a different one for the validation on each particular case, and a different set of 999 for your training on each case. If that seems extreme, it probably is extreme, but it may well be useful to do that as the ultimate test if you have the time and the resources, and your model is within a reasonable amount, and the application is important enough, mission critical enough to be able to test it. Okay, so that's called a leave one out. And there are different versions of this: leave 1 out, leave 5 out, whatever. Okay. Now, this then brings up the question of, okay, so that's fine, I'm training one hyperparameter. What if I've got multiple hyperparameters? What do I do? So let's say I've got the degree of polynomial, but I've also got my lambda value there. Okay, so that's 2, and in other systems I might have multiple hyperparameters. How do I train them all? How do I tune on them all? So it's clear to see that if you have multiple hyperparameters, it is difficult to choose the optimum for each, because what you've got to do is you've got to hold all the other hyperparameters steady while you test one of them. And then the question is, well, okay, if I hold all the other hyperparameters steady, what value do I hold them? So the problem is here with regard to this idea that if you have to hold all of the hyperparameters steady while you train one of them, or while you tune one of them, what value do you hold them steady at? So, well, what you have to try and do is you have to try and do every combination. So try every combination of each one and hold it steady at each of those values while you train all the others. So that means, let's say if you've got three hyperparameters, you're going to have 3 to the power 3 or 9 different trainings that you're going to have to do in order to train those. And in each case, you're going to have to vary those hyperparameters in each case. So you're going to have to multiply by 9 whatever many you were going to do. So you can see the problem that you quickly it goes up to that, and then you're going to have to try and pick the best point of the three of them. So you're going to have some way of plotting that in order to do it. So there's a little bit of thinking that's going to have to go into that. I'm not going to go into any more detail on it on this. Part of the thing that I want to kind of cover by this in this module is to give you a whistle-stop tour of as much of machine learning as I can, because it's a very large area, and for you then to know, okay, if I find myself in this problem, I'm then going to have to go and look into exactly how I'm going to do that. Okay. So hopefully with the assignments you'll get some of the kind of craft skills that go with it, but there just simply won't be time for you to get them all. So don't expect to be absolutely expert by the end of this. Now, when we're dealing with large data sets that take weeks to train, you can see that this becomes infeasible. Okay, that you can't possibly do all this cross-validation and all that if it's going to take weeks to train, or you're going to spend literally years trying to do it. So with small data sets, this can be difficult. You can have the opposite problem. It can be difficult to split into train, validation, and test, and have a reasonable number of samples in each of them in order for your model to be reasonable. So as you can see, there's no real perfect solution here, but nonetheless, depending on the situation you're in, you have to make the best of it that you can. Okay. Okay, can I check that you're all still with me? Because obviously my monitor has broken here. Yeah, you're all still there. That's good. Okay. So we're going to finish with a little small little exercise for you to have a think about. And what I'm going to pretend here that I'm doing is that I'm going to say, and by the way, I've just made up these numbers. They're not in relation to any particular model or otherwise. And in fact, one of the acknowledgements here is Nando de Freitas. In one of his lectures, he does something very similar. So that's kind of where I got the idea of just giving this a go in terms of the lecture here. So he used a different set of numbers, but same sort of idea. So what we're going to do is we're going to look at 5 different values of our hyperparameter lambda for our regularization. Let's say, for example, we're trying to decide how much regularization to use. And we've tried each of these different values, and we've trained until convergence. And then we've done a validation on that. So we've checked with our validation set. And the loss that we've got in each of these cases, and remember, this would just be the squared loss. It wouldn't include... it would not include the regularization at this point where we're comparing these two. So these numbers are somewhat arbitrary that I've picked here. So let's imagine that you've got a train error that goes something along the lines of 100, 15, 10, 1, 50, and your validation loss is 10, 5, 10, 100, 1000 for each of these different combinations. And just to state that this is a loss, so therefore a low number is good and a high number is bad. Okay. So let's say, for example, that you were then asked, having looked at this, then maybe this is your own model or something like that, and you're then deciding, okay, what value of lambda am I going to use? Which would you go for? A, B, C, D, or E? And I want you to just type one or the other in. I want you to choose something. Don't opt out. So Stephen, what I want to know is here we've done 5 tests of training our system with 5 different values of our hyperparameter lambda at 0.001, 0.01, 0.1, 1, and 10. We've got a training loss here in this column here, and big numbers are bad, small numbers are good, and we've got a validation loss here in the second column. And my question is, which value of lambda would you go for? Don't worry about getting it wrong, obviously. Okay, I think nearly everybody's taken a go there, and Blaheen's changed their mind. Okay, which are perfectly reasonable to do. Okay, so there's no, by the way, there's no absolute right answer here. These are more kind of rules of thumb. So I said to you earlier that we might suggest that the lowest value of the one that gets the lowest value of validation might give you the impression that that has the best generalization error. Okay, and that might suggest that B would be the one to go with because it's got a 5. But validation is generally a fairly small set compared to training, and you can see that training has got to its lowest down here at D, but obviously it's got a very poor validation at that point. So that might suggest we're getting towards the overfitting end of things. But what about this one in the middle where training is 10? God, I think everything is going to go wrong on me tonight. So training is 10, and I'm back up to me. Okay, so training is 10 and validation is 10. So what about that one? So let's see what people went for. We can see that a lot of people went for B, and that's reasonable. 0.01 from Patrick is B as well. And we've a few C's there. I think some people have D there, okay, which is the lowest value of training, which might sound fine, but you can see I'm getting slightly concerned, obviously, about the validation loss going so high at that point, which might suggest that overfitting at that point. Okay, so one of the solutions to this, and there are kind of 2 common solutions that we would use, is firstly go down the list and find which is the maximum number in that particular row. So the maximum number here is 100, between 110. Okay, so between that and that. Okay, the maximum number here is 15. The maximum number in this case is 10. The maximum number in this case is 100, and the maximum number in this case is 1000. Okay, and then in this column, what we do is we find the minimum of the maxes. Okay, so this is normally known as the minimax function. So what's the minimum of the maxes? It's the 15. Okay, sorry, it's not. It's the 10. Apologies. It's the 10. So under this system, we would maybe pick this one here, which is kind of given, it's allowing us to say, okay, we're certainly not ending up in the situation where we're picking that one. Okay, because what we've got to do is find the minimum of the maximums. And so this is one way of doing it. The other way of doing it is to take the average. So if we were to take the average of A there, it would be at, what would it be, 50, 55? 55, I think. Divide 90 by 2 and add it to 10, yeah. Midway between these two is 10. Midway between these two is 10. Midway between these two is going to be about 51, I think, or 50. And midway between these two is going to be where? Just slightly over 500 somewhere. So 500 and something. 500 plus. Okay, in this particular case, if we went for the average, we would either go for that or that, which is fairly reasonable, as you can see there, because a lot of you went for B for fairly good reasons. It had the lowest validation error and it had a fairly low training error. And then obviously C matches with what we chose last time. So you can see that if you were trying both of these methods and you found that actually this worked for both of them, you might be inclined to go for this. You might also be inclined to say, maybe our ideal value is somewhere between those 2 points. So you might be inclined to try 0.05 or something like that in order to see if that one would fit. Okay. So these are the sort of things that might be no harm for you to try out whenever you're trying your models in order to tune your hyperparameters. Okay. So we leave it at that for tonight, guys.